We got Blagovest Taskov here, who is a team lead at V-Ray GPU, and he's going to tell us some pretty hardcore stuff about parallel programming. So please welcome Blagovest.
Hello, so this is a talk about parallel programming. Before we start, a few words about me. I'm working in Chaos Group for almost 7 years now, and I'm the lead V-Ray GPU developer for about 3. I have some experience in the game industry in the past, and also I've led a course in the Faculty of Mathematics in Informatics in the Sofia University, and the resources of this are available online for everybody that likes to check. A few words about Chaos Group. We make tools for visualization. The most famous one probably is V-Ray, but we have V-Ray and Corona, which are photorealistic render engines. We also make Phoenix, which is a fluid simulator. We have VR Scans, which is hardware and software for material scanning. And we have PD Player, which is a professional player for image visualization. Not long ago, we got an Academy Award for one of our products, V-Ray. And I would like to show you some of the work that our clients have made during the past year using V-Ray. Just to get a sense about what we do, and it is also related with the parallel programming a lot because it's not possible without it. I cannot show you the whole thing because it's rather long, and we do not have that much time, but you can check the rest of it in YouTube if you like it. Okay, there's a few more minutes of this, and if you like, you can check it in YouTube. So now, when we clear this up, who is this talk for? The talk is primarily for students in university and high school that are familiar with programming, at least to some extent. Just in case this is not going in depth into many details. So it's not for parallel programming experts, nor it has anything to do with V-Ray GPU or any of the other Chaos Group technologies. It is a generally purpose programming talk. So before we go into details of the talk, I want to quickly mention something that I think it's rather important, and that's the question why and its answer. Now, it usually it's rather easy to find the answers of the questions what and how. Imagine that your program crashed and you got a no pointer exception. You know what is wrong. You are dereferencing a no pointer. You know how to fix it. You have to add a no pointer check. But the important thing is why it has happened. And usually, if you know why, you can figure out how and you can figure out what to do. Finding out which buttons to press or what buttons to press in a program or application to make something is easy. It's easy to memorize, but it's not the important thing. If you cannot answer why this is making the thing that it's making, it means that probably you're not doing something correct. And I have a pretty good example. When I was in high school, I knew what a discriminant was. I knew how to compute it, but I had no idea why this is working. I knew what it means when it's 0 or when it's negative, but if like the knowledge of how a discriminant is computed went away from the universe, I had no way to figure it out myself. It was something that somebody tells you how to do it, and that's all. Later in the university, discriminant became determinant. This was another thing that everybody of my colleagues knew how to compute, but had no idea what it means. We know all the rules, we know the theorems, but we had no, at least to my knowledge, there was no intuition about what this number is. And it is still quite helpful to know the rules because you can pass your math exam, and this is also important, but there are far more important stuff than this. A quick mention, if you're remotely interested in math, this YouTube channel has a lot of answers to the question why and gives a great intuition about many math concepts, and personally I learned a lot of it. Also, another thing worth mentioning is that you are the ones responsible to get the answer to the question why. You're the one responsible to ask your teachers, your colleagues, your lectors, or whoever this might be, and you should never give up until you find the answer of this. So, why parallel programming? We will talk about this most of the talk. So, short answer, so we can go to lunch, is that no matter how fast computers you have, people will always need a faster computer. For example, and also there is no other way to get faster computing these days but doing parallel computing. For example, a movie, Toy Story in 1995, was rendered about 4 hours a frame. There are 24 frames in a second, and it's about the same in 2018. Now, this in 1995, it was rendered on a computer much slower than your phone. Currently, the computers are hundreds, possibly thousands times faster than this. And it still takes 4 hours, not because the software got worse, but because people always find ways to put more data in it to process. Now, the movies these days, they're more complicated, there are more stuff going on, there are more explosions, they're more rich. And no matter how fast computer you have, there will be always a task that needs a faster one. Another thing from Facebook, improving the PHP JIT compiler by 1% results in many years of salary for their best paid engineers. And this is only from electricity savings, not accounting for better user experience, better e-commerce conversions, and stuff like that. Now, Google has made a research a while ago about benchmarking different languages. And they found that picking your programming languages matter. It matters to quite a big extent in the tests they make, on the programs they make using the standard libraries of each of the languages. C++ was 6 times faster than Java and 7 times faster than Go. Another thing to show this is a benchmark of web servers. You can see that the ones written in C and C++ are about 10 times faster than one written in Node.js. Now think about it. 1% matters this much, and now we are showing that just picking a different programming language can lead to much bigger performance improvements. This here is from CPP talk, where you can, I'm not sure if you can see the red pixel on the far right, but this is the straight C++ 98 performance. Like, it's not purple, it's red, but it's only 1 pixel. The blue and the purple are coming from taking different ways for parallel computing from the underlying hardware, like intrinsics and multi-threading, and the green comes from using a GPU, which is another parallel processor. Now, this is not true for every task. This is true for some tasks, but you can get a feel that there is much more performance hidden somewhere in your computer that you probably imagine. And now keep in mind that C++ that was many times faster is this red pixel. And the other thing is other stuff, not standard C++, or at least not standard C++ 98. The domain for such applications is rather big. All kinds of simulations, VR, AR, automotive, mostly all the fun stuff that you can do. The rest of the talk will go about trying to show that performance equals parallelism these days and efficiency equals locality. This comes from a talk a while ago by NVIDIA, and I will go into details about it. Before we get into that, there are only 3 ways to make something faster. And I'm not talking about programming, I'm talking about life in general. no matter what you do, to make something happen faster, you have to work faster, work harder, work smarter, or get help. Imagine that you have to paint a house. You have to paint the walls, you have to paint the floor. There are three ways to make this faster. First is just getting the brush and painting as fast as you can. Second is being more efficient about it. For example, imagine that there is a barrel with a paint in your basement. So it makes sense to have a bucket with paint close near you so you don't have to go to the basement every time when the brush becomes dry. And it's rather common sense. And the last thing is getting help, like calling the neighbor or calling friends. Now, getting help is tricky because imagine that while you're painting the wall, your neighbor is painting the floor, and now you're locked in a part of the room and you have to wait for the floor to dry up. And this shows that getting help is not as easy because you might actually do the work slower, not faster. Translating to programming, work harder usually means increasing CPU frequency. Work smarter usually means caches, branch predictions, and other stuff like that. And getting help means getting more cores, at least these days. We cannot increase, by we I mean the humans that make computers, they cannot increase the CPU frequency because of something called power wall, and I will show why in a minute. At some point, the bucket is as close as it can be. Even if you move it 5 centimeters closer, it doesn't make more difference, and this is how the memory wall works. The bucket is as close as it can. But the third one, get help, and putting more cores kind of still works. Now, I will not go into much details about these graphs, and you can bing for them later if you like. But this shows that the tiny switches from which the processors are made, called transistors, doubles every few months, at least up until recently. When the number doubles, it means that they get smaller, and when they get smaller, it means that they can switch faster. So this was how people were making faster and faster processors up until recently. Like making the transistors smaller, there's a way to make them switch faster. Now, this happened, which basically means that if you want to continue to increase the frequency, the CPUs or the processors will get so hot that they could not be cooled down. I will not go into details about these formulas, but you can check them later. And just to show that they're really getting very hot, you can see that in 1992, the watt dissipations per square millimeter in processors was about 10 watts. And in 2005, it's about 120. And this also is exponential. And this gets really bad. Here on the y-axis, we have the same watts per square centimeter and the time on the x-axis. And you can see the trend about the CPUs dissipating more and more power per square millimeter. And it is pretty clear that this has to stop at some point because this in the blue is the heat dissipation for a nuclear reactor. And if we keep this trend, you know that you cannot cool a nuclear reactor in your desktop machine or in your pocket. So what is important to remember is that at least up to until recently, the number of transistors kept going up. They keep getting smaller, but at some point, this blue here, which is their frequency, was capped. These days between 3.5 and 5 gigahertz. And it's not going to get much faster than this. Before we move forward, a few words about what is parallelism and what is concurrency. Now, parallelism and concurrency are often used in similar contexts, but they mean different things. Imagine that you have town A and town B, and you have a road with 2 lanes and 2 cars going from town A to town B. This is a parallel process, meaning that at any given point of time, both of the cars are progressing towards their goal. Now, if you have only one driver and 2 cars and the same 2 lanes, what you can do to move the 2 cars from town A to town B is the driver goes into car A, then drives for a while, then walks back to car B, then drives for a while, and so on and so forth. And this is a concurrent process. It is not happening in parallel, but you have at least 2 tasks which are both processing towards their goal as time goes by, but not necessarily at the same time. All right. So to figure out if you have good intuition about parallelism and concurrency, you have to think of an example where parallelism works without concurrency and the opposite. But this is rather food for thought. Now, single thread improvements over the last many years were about almost 3,000 times. And for the next 50 years, they will be optimistically up to 30 times. This means about 2 to 15% per year improvement for single thread and 75% per year for multi-thread. And actually, these are quite optimistic numbers because these days we're getting lower than this. Now, what you can see here is from imagine that this is a modern processor, about 20 millimeter large. This is a rather big one. And this here is 1 millimeter. So as we figure out, efficiency is important because of the thermal problems that we talked so far. What is interesting is that moving 64 bytes of data, 1 millimeter across this, is costing more than doing math operation on them, which means that moving the data is way more expensive than probably everything else that you can do. And we get to the second part of the talk, which is efficiency equals locality. And this is true both for serial and parallel programming. Now, the world is not flat, and I think that a big part of the object-oriented programming is denying that. Also, a lot of high-level languages like Python, Ruby, Go, Haskell, Java, JavaScript, C#. What I mean is that the only purpose of your program to exist is to convert one piece of data into another piece of data. So all you're doing is converting data. And object-oriented programming, one of its core principles is to hide the data from you. And I don't see how this can be a good idea. I'm not saying that it is a bad idea always, but what I'm saying is that it often is, and people tend to abuse it. Here is a cool graph that shows how much faster the CPU got over the years and how much faster the memory got over the years. And you can see that the gap in 1990 or in 1960 or 1970 when the object programming was invented was non-existent. The CPU was as fast as the GPU, but this is not the case today, by far. And hiding the data in the past wasn't so bad for you because it wasn't expensive to use it, but now it is. Just to have a feeling about how much expensive it can be, imagine that the CPU cycle takes a quarter of a second, like you have, like scale up the times, the frequency of the computing. So if a CPU cycle takes a quarter of a second, then reading something from the main memory currently costs 3.3 minutes, and reading 1 megabyte sequentially from SSD is almost a month. So the CPUs are much, much faster than the memory. So in the past, it was hard to make a complicated app because there were not many tools, not many frameworks for that. But once you make it, as time goes by, because the hardware gets faster and faster on single thread, your app gets faster and faster. So it was hard to make a fast application. Today, it is rather easy to make a complex application. There are many frameworks about it. But the differentiating point here on the modern applications is how fast it can run. Because making it just being complicated is not as easy as it used to be. It's not as hard as it used to be. Another thing to mention is that hardware is always defining the trends about the IT industry goals. It's, at least in my opinion, it's never the software. There are many examples about it, which I have no time to talk, but catch up with me later if you want to hear more about them. For example, now everybody is talking about real-time ray tracing. It's not about new algorithms were invented. It's about we got mainstream GPU hardware with it. And this is from Microsoft. Concurrency is the next revolution in how we write software, the same as object-oriented was many years ago. Now, let's talk about GPUs and how GPUs can help you solve a general purpose problem. So imagine that you have to write an algorithm that sorts numbers. Probably you will implement some version of quicksort, which is n log n, or something like this, or close to n log n in most cases. And this is good. This is very good sorting algorithm. But if you know a bit more about the input data, you often can design much better solution than the general purpose one. For example, if you have a few million numbers, you know that you have only a few million numbers, and you know that they're all integers between 1 and 100, you can implement much faster working algorithm, for example, counting sort. And this comes to show that knowing a bit more about the problem allows you to design much more efficient and much more better solution. So the GPUs know more about your problem, or they assume they know more. They assume things about your problem. They assume that it is embarrassingly parallel problem, which means that it is trivial. Embarrassing parallel problems are problems which are trivial to be solved in many cores or many threads, talking thousands of threads. Now, how many problems are embarrassingly parallel problems? Well, it turns out that quite a lot of them, actually. When the only tool that you have is a GPU, everything seems like an embarrassingly parallel problem, and people have invented ways to solve problems that seemed serial in parallel. Just to get a sense of scale, this is a rather modern i7 CPU, and you can see that the thing that handles the single core part is this, and more than half is about parallel computing. And actually, in this single core part, there are also a lot of hardware about parallel computing, different types of parallelisms. So for particular tasks, GPU, knowing that you have embarrassingly parallel problem, can give far better performance than CPU. Here you can see the green line is the performance of the GPUs. And the blue line is this theoretical performance, so it depends on task to task, of course, but nevertheless. And the blue line is the performance of the CPUs. Now, that's good. It means that solving problems in parallel can be quite efficient, and it can help us a lot. But there is this problem. So imagine that you have your application. In every application, part of it is serial, and part of it is parallel. So imagine that 50% of your application, 50% of the time of your application goes into the serial, and 50% of the time goes into the parallel. Now imagine that this parallel part is embarrassingly parallel, so you can run it on as many cores as you like. So if you run it on infinitely many cores, this 50% will go down to 0, but then again, your application will be sped up only twice, because the other 50%, which are the serial part, are still there. And this graph shows exactly this. Now, if you have 50% parallel portion, no matter how many processors you have, you cannot get more than 2 times speed up. Here on the y-axis, we have the speed up. On the x-axis, we have the number of processors. Now, if you have a very parallel problem, like you can do 95% of the time in parallel, you can see the green bar, which shows that no matter how many CPUs you have, you cannot make it more than 20 times faster. And this is kind of depressing, because we know now that people will always need faster and faster computing, no matter how much the computers are fast at the moment. And we know that there is no other way to get performance than being parallel. So this means that we are kept by the times of speed up. But this, luckily, is not quite the case because of this graph. And you don't need to look at it rather than it's linear. But what this graph tells is exactly with what I started, which is that when you make faster computers, people can always find bigger data to run on them. When you have faster computers for rendering, people will make the scenes, the movies more complex, which means that, in a sense, at least for some problems, the parallel part can grow infinitely. Because as it gets more and more powerful, people are finding more and more data to run on the parallel part. And this is true for at least some of the problems. Actually, this is true for many of the important problems in the programming. This is called Gustafson's law. So if you want to check it later, you can. So now we get into the boring part, which is how to do parallel programming. There are many different flavors of it. There are different types of parallel programming for CPU and GPU, but mostly the common thing is that you need some kind of low-level access to the hardware. And for this, you need a low-level language. I'm particularly using C and C++. There may be other languages which are better or not. I don't know because I don't have much of experience with them. I really don't like C++, at least modern one, but there's a way to get job done with it, and I'm not sure there are too many ways with other languages to do it. Probably they are. Then the most common types of parallelism in the CPUs are data level and task level. Now, task level is more familiar to most of the people. It is multi-threading, multi-processing, stuff like that. Data level parallelism allows you to extract parallelism for a single core. There is a way for a single core to do more stuff with the data you have, or to run more than one instruction at any given cycle. And there are some ways to do micro optimizations about this. Now the GPU, and this is true for all CPUs, by the way. It is true for, not all, but most, like all the CPUs in this room. I'm pretty sure it's true for them. It's true for Intel, AMD, all flavors of ARM CPUs as well. For GPUs, it is a bit more complicated because in order to make a program for GPU, you need to use a particular API. And these APIs can be very vendor specific. I've put here the most important ones, so you can search for them. But basically, we have CUDA from NVIDIA, which is quite popular, runs on every operating system, but mostly it runs only on NVIDIA GPUs. There are some ways to run it on other GPUs, but officially it runs only on NVIDIA GPUs. The OpenCL should be the open alternative of CUDA, but it is. It runs on all kinds of GPUs. It somewhat runs on NVIDIA GPUs because it's not very well supported there, but unfortunately it got deprecated in the Apple computers recently, and fortunately it is less flexible than CUDA, so it can't do all the things that CUDA can. Now there is few more open initiatives like Vulkan Compute, which gets popular recently, but it's rather new, and I cannot think of any general purpose Vulkan Compute application at the moment. And there is Metal from Apple. It runs on all hardware, including Apple designed GPUs, but it is available only on Apple operating system, including iOS. So this means that there is no silver bullet here. Different APIs are good for different tasks, and it will depend very much on your hardware and case which one to use. So all the APIs, they have like server client view of your computer or server view of your computer, where the CPU orchestrates multiple devices, multiple GPUs, and basically all the APIs, you can prepare some chunk of data, send it to the GPU, then ask the GPU to run some program on it, and then download it back from the GPU to the CPU. This is basically how every general purpose compute GPU API that I've seen works. And also all of them are based on C. There are a few of them support C++ a bit, but every one of them is basically C99 plus some extensions. So for some reason, showing few lines of code that can do a lot of stuff seems to be very trendy, so I did this as well. We have a CPU and GPU code that perfectly scales up to thousands of CPU processors or GPU processors, which finds the square root of an array. And you can see that it is very easy to do, like do not be afraid and play with it. All right. Where to go from now? The best place where you can learn more about efficient programming or parallel programming, in my opinion, is the Sofia University and the Faculty of Mathematics and Informatics. And I'm saying this because I feel like from all the noise that happens from other places, it's kind of we tend to forget that. Now, there are a bunch of references. about the data that I used in the talk, which will be available later for you to check. And key takeaways, start with why. Performance is important.
That was great. So we have 10 minutes for questions. And the food is still not going to be served until we finish the time for questions. So please don't leave. First question. Somebody? I have a question. So, what is the best way to start for you dealing with some a little bit hardcore multi-process and multi-threading? So you showed FMI as the source of knowledge, but any starter tutorials, any online courses, something?
Yeah. The best way to start is to open your favorite search engine and type parallel programming. I have a lot of references here about free. I showed the references slide. In the references slide, there are a lot of free online resources about it. There are a lot of papers and books, which is what I recommend for getting familiar with the topic.
Great. Some other questions? There is one.
My question is, actually, if you have data parallelism and process parallelism, which of them will bring bigger performance? Something between them, all of them?
Okay. Usually the only answer that I've heard every time when somebody asks something about performance in computing is, it depends. It always depends. It depends on, of course, on your problem. There are problems which are rather easy to get data parallelism from. There are such which are not so flexible. Of course, if you can use both, and if your hardware have both, you have to use both. But apart from this, I don't have a general answer that works for in the middle case.
Great. We have one more question here.
Hi. I want to ask you how often do you dig down to JIT intrinsics and compiler-generated code in your regular work?
So the question, can you repeat it? Because
how often do you dig down to compiler-generated code and JIT intrinsics and maybe some hardware-specific code in your regular work?
Okay, it's a very good question. So how often you have to deal with compiler intrinsics and look at the generated code? The only way to know about how your program looks is to look at the generated code. Now, usually you don't do this very often, but if you really care about a piece of code, you have to look at the assembly to know what happened. Compiler intrinsics, I especially do not like them because they're not portable, which means that if you write them for one CPU, they will probably not run on other microarchitecture. Apart from that, there are good libraries or frameworks, or you can make one yourself that wraps these intrinsics into something that is portable and that translates to code that compiles on more than one CPU architecture. And this is something that we do a lot at Chaos Group. We have a lot of, all of the important code in V-Ray is done with a library that wraps intrinsics for data parallelism everywhere where this is applicable. And usually, yeah, you have to deal with those because the auto-vectorizers of the compilers, they're good, but they're not ideal. And you can get much more performance by doing it yourself.
Great. And we have time for one last question.
Hello. Thank you for your talk. I wanted to ask you something because half of the talk and the presentation was quite related to what comes next with processors and the future about their productivity. what's your take on quantum computing? Currently, the world is separated like optimists, pessimists, etc. So what's your take on this, and how do you think it will impact the topics that you discussed and the problems that you're currently trying to solve in different ways? Thanks.
Okay, so there are two questions. First is the optimist versus pessimist. I'm not much, it is, the second part of the question is more about hardware, and I'm not very fluid in that. But I've watched an interview about, with a guy that works in one of the factories, and he said that back in the 1990s, I think, nobody believed that they can go under 100 nanometers or something like this. And he said that during his career, he's heard a lot of times where people were confident that this time the progress will stop, and that the optimism is the only thing that moves this industry forward. Regardless to the first part of the point, how I do feel about it, I have a general rule of thumb that low latency processors are around 10 times less efficient than high throughput processors, and high throughput processors are about 10 times less efficient than fixed function, which means implemented in hardware, which means that at some point, if you continue to have more and more transistors for something, and you cannot get more parallelism any other way, it makes sense to have your algorithms, at least the most popular ones, implemented in hardware. And I think this is what happens, for example, with the GPUs. Recently, we got the hardware for ray tracing, for ray scene intersection, which is a complicated algorithm, which is often needed, and now we have it implemented in fixed function. And I think that probably, my opinion, is that probably this trend will continue.
Great. I think we have time for one more question.
Hi, I would like to ask, what are the best techniques you use in order to ensure that most of your code is parallel?
Well, I have the luck to work on a problem that is embarrassingly parallel, so it is very trivially to make it run in parallel. Now, best techniques is, well, there are two things which are important for every application. First is, does it run correctly? And this is the most important one. And for me, the second most important one is, does it run fast? So the common sense is, you write the code, you check it if it works, you check it if it's as fast as you want it to be, and if so, you're done. You can write it in every language you like. You can write it probably in Python, in Ruby, it will be much easier. So if this is fast enough for you, you're fine. Then if it's not, you have to figure out why it is not as fast as you like. Is there a parallel part that you have to look about something in your algorithm to see if you can done more efficient or in parallel. Now for C and C++, there are many tools. There are tools from Intel, from AMD. There are many tools for Linux that allow you to profile where your program spends most of the time. For GPUs, there are some tools. They're not that good yet, but they're pretty good. So the next thing that you do is you never optimize anything without knowing which is the slow part. You find the slow part, and then you optimize it. You never assume. Assuming is very, very bad idea. And then if you make a change, and it does not improve your code, usually the better practice that I know is to revert it, because you only want to keep in the code any additional complexities that have some benefits for the end user. So yeah, this is it. First, you write it. If it's fast enough, you're done. If it's not, you have to figure out why. I don't know how profiling works in high-level languages. And when you figure out why, then you continue to work on that part.
That was great. Thank you, Blago. One more time.